group doing exciting stuff with conservation genomics. And I think he's more or less continued in that line of research. So since then, he's moved on to Brown University in the US. He's an evolutionary biologist interested in studying. Sorry, I'm getting some feedback from the YouTube channel. All right, sorry, we're back. So, as I said, he's an evolutionary biologist interested in studying signals of selection. And today he's going to talk to us about one of his more recent endeavors during his postdoc at Brown University, looking at the application of machine learning techniques for picking out or detecting these signals of selection in coding sequences or in gene sequences. So I think he's got a little introduction prepared, so I'll just pass the mic on to you, Carlos, and take it away.
Thank you, Chris. Can you hear me well? And you can see the arrow point around here, right? Okay, so first of all, I want to thank my research center, EBD. I still consider it mine. Still have so many friends and colleagues there. On the reception for this talk, which is finding selection in everyone, everywhere, all at once. And the choice of the title is not artificial or random. The introduction that I wanted to make is simply what I'm working at right now. So this is the city of Providence. I'm working at Brown University at the lab of Sohini Ramachandran. It's mainly a center for computational molecular biology, so it's not so much centered in conservation anymore, but more into developing methods, bioinformatics solutions, and implementing algorithms that can help in resolving certain evolutionary or medical questions. Right now I'm working in detecting selection, and the center is most centered, even though there's all kinds of research there, so can be wild species, can be with domesticated species, ancient DNA, parasites such as vectors of transmission of diseases, single cell genomics, and in particular case, I'm very interested in detecting genes and their selection. These are three populations that are under extreme abiotic pressures, namely Inuit in Greenland, which receive extreme cold, Aboriginal Australians, which receive extreme heat, and Bolivians and Peruvians of the Peruvian Altiplano, which is a certain level of hypoxia. This is just to illustrate what I'm working at, so which genes could those populations have selected. But actually my work is applicable to everything, and what I've always wanted to do while I was here is to try to connect what I'm doing right now with conservation. So as Chris said, I did my doctoral thesis in EBD working with this beautiful animal, the African golden wolf. And I never lost track of what I have been working at before and try always to connect to what I do now. So just to start a little bit, we know we live in a changing world. Climate change is inevitable now. Sadly, we have been years and years saying that we can still revert it back if we all make a little bit of effort, and there's still some room for hope. But the change is already here, and we have processes of desertification and deforestation and habitat fragmentation that are going to inevitably affect lots of wild species. Also, there's this kind of projections that we can kind of forecast how changing of temperature is going to be in the future, and how animals or any kind of species that live in these areas is going to be affected in the future. So species have a range of ways to adapt. We can see how, for example, in the ecosystems, the species interaction can change. Some species can disperse into colder areas when there's when warming is affecting their particular area of origin. There could be some extreme demographic changes that still maintain the genetic structure or so to say, the genetic diversity of the species. We could have some physiological adaptations, some use of environmental links, and finally, evolution. But the question is how quickly those species can adapt, because we know that, for example, in a mountain range, so if we speak about displacement, certain species that live in warmer areas would eventually move gradually to colder areas for latitudes, but there are certain species that are so adapted to their former conditions, the cooler conditions, that they won't find any habitat at all when this change is going to come. The idea is how physiological changes have also obviously limit, right? So the idea is how much time do they have to adapt? Can they still adapt anyways? And this is a plot of species. How many species have been extinct since 1500? Most likely the number is much, much higher, but this is the ones that have been discovered. This is an example of one species that was just extinct last year. And the idea is to try to study, conserve as many species as possible, also the genetic diversity and the evolutionary unities of conservation, so to say, and try to avoid events like this to happen in the future. Some species are able to adapt rather quickly, like for example this one. As you can see in this plot from the 1950s to the 2000s, the proportion of individuals in this particular group of species with a certain phenotype has changed. So that means that there was an underlying genetic variation that allowed them to adapt to the conditions when the environment changes in such a short amount of time. But also not always this is the case, and species that, for example, have longer generation times, we have events like this one, for example, in which Arctic foxes are mixing with red foxes, or polar bears with grizzly bears, so what is called now grizzler. And we have to mention that hybridization is also a way of certain species that are highly adapted to colder conditions to just escape extinction. Even though that brings a plethora of different problems, such as pleiotropy, in which hybridization between a species that is adapted to an environment with another one that is not. Recombination can, for example, alter the patterns in which, so the genomic structure and finally the way those genes interact with each other, because they're not coming from if in the same species, the genes are connected to each other in a metabolic path or a regulatory path. It could happen that those genes are not together anymore. So hybridization is also a source of variety, but also could be a source of impoverishment of the genetic diversity of the active species. This is a case that the case that I know the best, the African golden wolf. This is the range of distribution of the African golden wolf in Africa. As you can see, the majority of it is in the desert of Sahara. And even though in so many cases we're speaking about with certain pessimism about how wild species are going to disappear or going to be affected in the future, in this case, in the golden wolf case, we have some positive outcome of the studies, and we have some room for hope for this species in particular. In general, though, it has been studied that it could be susceptible to climate change. So recent studies, this is in Tunisia, explore how through niche modeling African golden wolves could basically lose all of their possible distribution in Tunisia by 2080s. But it is important to know that, for example, this species has some potential for hybridization, and it's very interesting as a species because it became recently a top predator north of the Sahara, which means that its conservation could potentially help the conservation of entire ecosystems across the African continent. What we discovered in my thesis is that the African golden wolves could potentially not only be part of one species with one ecotype. Now, this is a PSMC plot. Some of you are familiar with it. This is the point of speciation of African golden wolf, so that's where still were a single species. Now, today still come from a single species because the lineages and groups of the wolf, which are distributed across the entire continent, the north of the continent, they're still mixing with each other. But as you can see here, these green lines represent the moments of green Sahara, in which we have a savanna, and these blue lines represent the moments in which we have a hyper-arid desert in the Sahara. As you can see, certain groups, certain lineages, had a decline during those green times and had an increase in population during those arid times, which I could use it as an evidence that they are adapted to arid conditions. However, other groups were more successful during those mesic conditions and were declining definitely during those arid conditions. So we have different ecotypes potentially of the same species that are adapted to different conditions. And when climate change arrived to some of the areas where still these lineages are mesic, some other lineages could replace those, and we could have some population replacement back from within the same species, which means that still the species is going to thrive and exist in those areas. When we study genes and their selection, we discover a number of genes that are outliers for the values of, for example, composite likelihood ratio statistics or NSL. And those genes are involved in a number of adaptations to the desert, such as energy and fat metabolisms. For example, it makes sense when an animal is spending a long time in the desert without any source of food, or reabsorption of water in the kidneys, heat shock proteins, DNA damage repair, protection against melanoma, and so on and so forth. So we could say safely that this animal is adapted to the desert. And this is something that we discovered using a number of statistics to detect selection. The problem is, are we looking in the right direction? If you look at the number of the papers that are studying wild species, there's a number of statistics that are used very often, and very often evolutionary biologists just look at the statistic that is mostly used in bibliography, but that doesn't mean that we're using an appropriate statistic to detect those genes and their selection, and maybe we are underestimating or overestimating the potential of that species to adapt to climate change. And that is a serious concern, because it could happen that we are informing actually conservation policies, and we are doing so erroneously, right? Just to have an idea of how which are the different models of how selection happens and how beneficial mutations rise in frequency. One good example would be a hard SWIF. So this is the classical example of how in a species, let's imagine those are chromosomes, or that belong to different individuals. There's a beneficial mutation that provides this individual more fitness, so that rises in the population until becoming the norm. It can happen that we are detecting this, but this SWIF hasn't finished yet, so it's a partial SWIF. It could happen that this species in particular, this beneficial mutation, hasn't become beneficial yet, and so it becomes transmitted randomly in the population. So there's a number of mutations that appear across along with this particular mutation, and the haplotypes are not that long. As for example, here that is the same haplotype basically, in which neutral or slightly deleterious mutations are hitchhiked along with this beneficial mutation. It can happen that then, after a certain number of generations or after an environmental change, this mutation becomes beneficial. So we have a number of haplotypes with the same mutation, but with different signatures of neutral mutations that are hitchhiked along with the beneficial mutation. And it can happen that it's a bit more difficult to detect, and this will be what is called a soft SWIF. And it could happen also that this mutation doesn't reach fixation yet, but we have a new mutation that appears here. Now, this is just to illustrate how different models of selection can give us different signatures, and it's not always easy to detect all of them at once. And in fact, I can safely say that we have right now around 40 or 50 different statistics proposed to detect those signature of selection, but each group of statistics is more specialized into a particular model of selection. So, for example, for hard SWIFs, we would have composite likelihood ratios-based statistics. We will have for ongoing SWIFs extended haplotype homozygosity-based tests, H1-2 in the case of soft SWIF, populations with different selective pressures, etc., etc., etc. I think the point is very well illustrated in which to say that there's so many statistics, and not all of them work the same way with the same demographic history and models of selection, that it is actually particularly difficult to distinguish when one statistic or another could be used in detecting selection in the organism that we're interested in. And this is crucial. If we are not able to detect appropriately the genes that are under selection, we could, again, overestimate the capacity of this animal to adapt to change, and maybe we shouldn't. We would not be spending all the efforts in this conservation that we should. This is, for example, just to illustrate how if we have the same kind of SWIF, which is just a hard SWIF, if we have a different beginning times of the SWIF, and this was studied with human population, so you would have to divide this by 30 or 25 to just take the number of generations. So that would be 1,000 generations ago. If you take different allele frequencies, so those are weaker or stronger selection, but just the same kind of SWIF and different times and different frequencies, different statistics are going to provide a different answer, and they're going to be more suitable to study this SWIF, which is very interesting. So with this, there's a new generation of methods, composite methods, that are actually using a combination of they use a machine learning based algorithm in which basically the function is very similar. So only the CMS is assuming that all the statistics that you're providing are independent from each other, and Swiffer doesn't so. So Swiffer is informing itself from the pairwise combinations of statistics. These statistics are actually providing it with more evidence. And Swiffer is able to take the information from all the statistics at once, just to tell you what is the probability of a SWIF in that particular region. And as we can see here, for example, these are receiving operating characteristics curves. This is the black, we want the true positive rate to be as high as possible and the false positive rate to be as low as possible. And this black curve would represent the potential of Swiffer, so the power of Swiffer to detect the SWIF. And this, for example, EHH is one of the most used statistics in the literature with wild species. This was performing like this. So as you can see, Swiffer using these statistics, because the Swiffer was gathering information from all of these statistics at once, was outperforming every single statistic. And a paradigm in machine learning based methods is the more information you give to the network or to the method, the more accurate it's going to become. So actually we can actually improve it with new statistics that are appearing every day. Actually, so easy to see some statistics, some single statistics that are widely used, FST, for example, XP-EHH or EHH, to be updated very quickly. Right now, from the top of my head, I can think of 3 or 4 new methods to detect selection or statistics that appeared just last year. So the idea is not to use a particular single statistic, but to use them all at once, having very flexible algorithms like software like this one, like Swiffer, for example, that you can put just all the statistics that you want and just see the outcome of it. A practical example was, for example, this one. In Cape Verde, there was a study by this Hamid et al. In 2021, in which they saw the Duffy allele that is basically is there's some certain variations of the allele that can help in the resistance against malaria, and the Cape Verde population is very prone to be affected by this disease because of natural conditions in the islands. They saw that these are the haplotypes of African origin that exist in the population and of European origin. So clearly, having longer haplotypes and higher percentage of ancestry from a certain source, it means that we have a certain allele here that doesn't exist in this population and could be an evidence of it being selected. And when they studied it with EHHs, they couldn't see how the Duffy allele was selected in this population, but once they applied SWIFR, it was very clear that it was. So the challenges mainly are what happens if, for example, if you have a mixture that will break the haplotypes. If you have extended haplotype homozygosity based methods, recombination will just break those haplotypes. If we have a mixture between animals or species that are adapted or not adapted to a certain condition. Demographic history events such as population contractions or expansions, or for example, decreases in heterozygosity overall, could provide blur signals of what could be considered selection, but it's actually not. This is something that I find very particularly interesting. Soft-SWIFs could be 10 times more often happening as hard-SWIFs, which is the classic model that we understand. Soft-SWIFs could be the genes that are going to be selected in the future that are not under a strong selection yet. So that can tell you actually what is the potential of these particular species to adapt to change. So understanding where those soft-SWIFs are is also very important. And the idea is, are we over or underestimating the species' potential to adapt? So the objectives of my work right now are detecting alleles under selection and mixed populations with a number of models that I'm going to speak about. See the performance of SWIFR and the complex demographies. Distinguish versus hard and soft SWIFs if possible, because SWIFR is able to inform itself from 3 different groups of simulations that I will explain a bit more later. And also the idea is to more or less inform which single statistics are well equipped for complex scenarios. Although, as we can see, not every statistic is able to perform equally well for all scenarios, and there's not a one that fits all statistic. So what I'm doing is performing simulations for a moment. I'm working with a number of scenarios in which I compare between different populations. One of them, for example, this one doesn't have any particular mutation that is beneficial. And population 2 would have one beneficial mutation that, since it provides more fitness to the individual, it would rise in frequency during time until it becomes more frequent in the population. This is from the past to the present. So this will be like the ideal scenario in which we have 2 groups, 2 populations. One of them has an adaptation, the other one doesn't, and there will be no admixture. In this particular case, when we get to understand admixture patterns, we would have, for example, one particular group, another one, and then through admixture that would give rise to a third one. But what happens if this third one is adapting itself to a condition that these 2 were not exposed to? And for example, we can find in a change of environment, we would still have a hard SWIF in which this particular beneficial mutation would rise in frequency in the population. This is an example of how the lactose operon, for example, worked in human populations in the Middle East 7,500 years ago, right? How certain populations domesticated cows and they were adapted to drink milk, and they were able to extract more protein from it, so they got given a fitness advantage. But actually the source populations where they came from didn't have this mutation. Now this is an example of adaptive admixture. What happens if we have one population in particular that already has this beneficial mutation, in which is rising in time. And then they, through a mixture with another population that is not adapted, they provide this gene that is under selection to the new population. This is an example, for example, how Tibetan mastiffs provided the EPAS1 gene that helps under hypoxia conditions in the Himalayas. They gave it to Tibetan mastiffs, right? Tibetan dogs didn't have adaptation before, but after they mixed with Tibetan wolves, they actually were able to breathe under hypoxic conditions. So this will be the example of adaptive admixture. This will be called scenario 2. In scenario 3, we were wondering the same thing. So what happens when one of the source populations has an adaptive mutation, but after environmental change, that mutation is not useful anymore? What happened, for example, with African American populations when some of the source populations, so 400 years ago, when Africans were enslaved and transported to North America, for example, they had certain adaptations against malaria, and malaria is not existent in North America. So is that gene still under selection, or after generations that gene becomes neutral or even slightly deleterious because the fitness advantage of having sickle cell anemia is not anymore to protect themselves against malaria? This would be a substrate based in standing genetic variation, so this would be a neutral mutation that would fluctuate randomly in the population through genetic drift until after a certain change could become beneficial. So this would be, for example, the genetic diversity of Africans before they left Africa 80,000 years ago was that there was the potential of having all skin colors possible, but only after migrating to higher latitudes where the UV light is slower, they actually adapted themselves to have less melanin to be able to produce vitamin D, so that the dimmer light, the UV light, could penetrate through the skin and produce vitamin D in the blood. This is an example with humans, but we have plenty of examples of any literature with wild species too, and adaptations. Finally, this is one very interesting example. What happens if we still have one beneficial mutation that is still beneficial from the source to the, let's say, daughter population, but it happens that it takes some time to reach in frequency, and meanwhile another beneficial mutation can appear. And this is an example of how, for example, Saudi Arabian populations, they received the alleles that allow them to drink milk, but the domestication of the camel, I don't know if it was 1,000 or 3,000 years ago, it allowed them to, boosted the appearance of another beneficial mutation that allows them to drink milk. So yeah, having all these models of selection in mind, all these scenarios, I am running 1,000 simulations to train the model of Swiffer, using 200 to just testing as dataset, and I've been testing it against the same demographic scenarios where, for example, this mutation will be totally neutral, and where I wouldn't have any selection at all. And I've been trying to train the model of neutral versus selected and see what happens. So in this sense, I am testing a number of statistics. The original 5 would be XP-EHH, NSL-IHS, FST, and BDAF. Each one of those names means something different. But as we said, you can use as many statistics as you want. That's the good thing of Swiffer. It's totally agnostic to the number of statistics that you're providing, and the more information you provide it, the better. So right now, I've been working with these 5 statistics, but I'm expanding the model to use it with more. And I've seen that Swiffer is more powerful than single statistics. That's something that we knew from before, but also it happens in scenarios where we have a mixture. As we said, IHS is one of the most used statistics in studies of wild species, and also FST. You can see what is the power of FST here, and also EHH here. But for example, SWIFR is just learning from all those statistics at once, and it's providing a much better evidence to detect those mutations. And also something that is very particularly useful to see is that, for example, NSL and IHAs don't perform well when the gene and the alleles in their selection are almost reaching fixation. So that's how you see this poor performance here, but still SWIFR is learning from all of them, and it's outperforming every single statistic that we use. So this is 20 generations of the onset of beneficial mutation. I provided a selective coefficient of 0.1, so super high. And this is 200 generations. So these alleles are almost reaching fixation, or reaching fixation in some of the 1,000 simulations that I ran. As you can see here, well, this is the difference between what is the distribution of values between the non-selected versus selected simulations. So this would be FST, and how you can see how gradually after the generations, this distribution of values of FST gradually gets separated from the distribution of values of FST where the simulations, so these scenarios where they weren't under selection, so they were neutral. But for example, in cases like IHAs, it's much more difficult to distinguish. IHAs and NSL provide a trimodal distribution, and it's difficult to differentiate from the neutral. However, SWIFR, right from the beginning, is able to draw a pattern very clear of, it could be also considered as almost considered binary, between the neutral and the selected. The potential of SWIFR is so that we can also use certain scenarios at the same time. I can use, for example, one neutral scenario, and we can use certain different demographic scenarios and models of selection, and see, for example, if I'm finding a hard SWIF or a soft SWIF, or an ongoing SWIF that hasn't reached fixation yet, or some scenario in which we used to have a beneficial mutation that has lost the advantage. And this is the example. So, for example, here I'm working with the neutral simulation and scenario 2 and scenario 3, and we can see how they are very well differentiated. Not so well in the case of other combinations of statistics. This is NSL versus DDR and FST versus XP-EHH. But the important thing is that SWIFR is still able to differentiate between them because it's learning from this plot and this plot at the same time. And finally, also if we can use up to 4 scenarios at the same time in which we're comparing them, for some statistics it won't be working, but for some of them is working very, very well. Scenario 2 is a bit more difficult to differentiate. Again, this is the scenario where we wouldn't be losing, so we would be losing the adaptive, the beneficial advantage of that mutation after admixture, but we're able to see this difference between these 3 very, very well. I'm still working on this. There's still many plots that I can show you, but it will take me days. And I just want to bring in the ideas, and also I want to focus on how important this could be for conservation. We can see that not only SWIFR is outperforming single statistics, but also even under admixture and complex demography. It can detect weak or strong selection, lower high-late frequencies, and few or many generations after the onset of beneficial mutation. And it's able to distinguish between different models of selection. To sum up, the next steps that I'm going to give in my work, once I have all the comparisons that I need with the simulations, the idea is to just move on to real-life models, very well studied and understood models with different genomic architectures, such as Drosophila humans and dogs, where we have very different karyotypes, and see how challenged the model is going to be. The idea is to also include more complex demographic changes, expansions and contractions, different mixture proportions, and so applications to any species that can have a demographic model. It doesn't need to be an exact demographic model, but it is properly studied, because that's something that SWIFR needs. And also I'm proposing a review and rethinking of all the previous works with wild species that have been crucial for the conservation efforts. If we are, for example, finding a study of species based in FST or IHS that is determining that this species is actually adapted to the environment and could be potentially resisting climate change in the future, I would propose to rethink those studies just to avoid, again, the underestimation or overestimation of the adaptive potential of that species with an ongoing climate change. So finally, I want to acknowledge especially my PI, Sunil Ramachandran, really brilliant person and an inspiring person to work with, and also Lauren Stockton, who is the person who was behind the design and writing the code for SWIFR. Also, super brilliant person and a person which is a pleasure to be working with, and also my peers, Sunil Ramachandran's lab, Elsie Gibson, Cole Williams, Brina Lopez de Feller, Kaylee Alquist, and Sam Smith, which really give me the joy of working there. So thank you very much, and if anyone has any question, I'll be happy to answer.
Okay, thanks so much, Carlos. Really interesting stuff. And as you mentioned, so any of you out there listening, if you have any questions for Carlos, I encourage you to put them in the chat in the YouTube channel, and I'll transmit them to Carlos. So while that chat heats up a little bit, I thought I'd get the ball rolling. So I think it was super interesting. I have some more specific questions, particularly about the input of the kind of input that you need for the models. But I think my first question would be, so in your opinion, is this SWIFR kind of the end all for? I mean, you've kind of sold it as, you know, the best by far detection method for signals of selection. You know, does that? I mean, it seems to blow out of the water all of the previous metrics that people have been using. So is this kind of it? Are we done? Is this what everyone should be using from now on, or do you foresee some problems with or limitations with this application?
Good question. Probably the limitation of SWIFR is that in order to be accurate, you need to provide a demographic model that you know of the organism you're working with. That doesn't necessarily need to be the case in the case of non-model species that their demographic models are still being studied. I'm going to work with one of my ideas is to see what happens if I have violations of the assumptions of the demographic model, and just to see if the accuracy or the precision that I can find or the power to detect those alleles on the selection is going to still be the same. But I think that SWIFR is not actually the last model that would appear, but is the new generation of models. So SWIFR is not actually using one particular way of detecting selection. It's using all of them that you want to give, and it's super flexible. So you can use as many statistics as you want. You can use the statistics that you want. The question will be to choose which statistics is the one that you want to use just to fit SWIFR. But I really see it as a potential cap, at least temporarily, until there's a new machine learning based algorithm that is more precise than SWIFR and can appear in the future. But since it's not a method on itself, it's just a compendium of methods, I see it as a possibility. Yeah, totally.
Okay, cool. And I mean, so that kind of segues nicely to my next question. I mean, so you've been focusing mostly on these simulation studies, and if I understood correctly, now you're going to try and take that in a more applied direction. So I was wondering if you could talk a little bit more about the kinds of inputs. So you already mentioned that the demographic model is very important. And I was wondering how, the applicability of these kind of models, especially since machine learning approaches, especially that training component requires or tends to require a fair amount of data. And, is that available for especially, rare species that might, be of conservation interest?
Absolutely. So what I'm working with right now, the simulations I perform is with SLIM. If you're familiar with it, or if someone from the public is unfamiliar, it's this forward-based simulation program that also has its own coding language, which is not difficult to learn. It's similar to R. The idea is that I'm simulating 1,000 or 10,000 runs, for example, and that's used as a training for Swiffer. And then I can use, once Swiffer is learning how this is working, and that's why it's appropriate to have a good demographic model, now you can fit in real data. So, for example, let's imagine we have one particular chromosome that we're interested in, that we think there could be a gene under selection. Or I can, for example, try to model the 38 chromosomes of the canis, so dogs, right? Then, after running my simulations, then I can actually use the real genomic data of dogs, or wolves, or African golden wolves, or Eurasian golden jackals. The phenotype is the same, so the structure is very similar. So I don't know if I'm reconnecting with your question right now.
How easy is it to get the data that you would need from different organisms to be running these kind of models?
It's actually easy. The simulation just requires you to have a certain knowledge of the genomic architecture of the organism. So just to have at least a proposal of a genome, or how it's constructed, and have a proposal of a demographic model. But again, I'm trying to test what happens if, for example, I am running a simulation with a certain demographic model, but the species has a different one. So what happens if my training and my testing data sets are different? Do I still have the power to detect it or not? That's the idea. But yeah, absolutely. Like, for example, this example that I put with the Cape Verdean population, I think the chromosome where this daffodil is the chromosome 8. So they just simulated chromosome 8 for 10,000 times, and then use the real chromosome 8 from the population. And the testing data set doesn't need to be so large. You don't need to have hundreds of genomes sequenced so that you know if there's selection in your organism. So yeah, absolutely. It's very, very available.
Okay, great. Thank you. So Carlos Villa has posted some questions in the chat. So first of all, he says that he thinks it's a very interesting and thought-provoking presentation, and is asking if it's possible to use this approach with fluctuating selective forces and also balancing selection.
Good question. I haven't explored the possibility of balancing selection yet, but it could be possible. Fluctuating balancing forces. We can actually simulate that. Let's imagine that, for example, we have the example of an active mixture, right? And in this particular case, one of the source populations is suffering different fluctuating, so the same allele will have different values of selective coefficient because of environmental changes across this time, no? Or, for example, one of the source populations can have that. That's something that can be very easily simulated with SLIM. And you just need to, at this point in time, let's say, 20 generations, for example, after the onset of an efficient mutation, just change the selective coefficient, and then continue, go on. After a number, so of course it will require some simulations. It will require some, if you want to work with different scenarios where the selective coefficient will be different according to your estimations or what you can think it will be, or what you can test, and then run with the real data and see to which training data set it looks more like that would be the idea. But balancing selection is something that I'm still working with Sohini, and we're still thinking about how to implement it. But we are positive in thinking that it could be. We're also including the possibility of background selection. So when we are, for example, if we want to simulate an entire chromosome, we want to take into consideration that the detrimental mutations are going to be 70% of all the mutations that we're going to find in the chromosome, according to some models by Eric Walter in 2008 or so. So we'll have negative and positive and neutral selection happening in the same chromosome. So, yeah.
Okay, and just sort of following up on, so Carlos is particularly interested in extreme fluctuations. So if you have examples where you have the temporary contractions of populations, that reach, effective number of individuals, or NE less than 10, and how that would translate, into bearing selective forces.
That could theoretically be affecting more this appearance of haplotypes, of long extended homozygosity in haplotypes. It could affect them more dramatically because of the appearance because of the loss of diversity overall in the genome. Than, for example, statistics are based patterns of frequencies in the selected alleles, and how statistics are affecting them. So how statistics are able to detect them better or worse. Like, for example, FST or TGMSD or so. So I was when he mentioned fluctuations, I was thinking about fluctuations of the selective coefficient and not of the population. So those fluctuations is something that we are also considering. What happens if we have expansions or contractions of the source population, or sorry, I just said something else, or the other population. So yeah, actually that's something that can be also simulated with SLIM. I haven't reached that point yet in my research, but I expect to do it very, very soon.
Okay, interesting stuff. So I had one sort of, I guess it's more of a point of clarification. I was wondering if you could help me understand. So if for those, your simulation results that you got for these, the performance curves.
Yes.
Yeah. So the two green lines, the EHH and NSL, I mean, there's like a lag, right? Or there's kind of a, before it takes off that curve. So I was trying to follow that, and I got lost. I mean, it's definitely not my topic, but they seem to be behaving very differently to the other metrics. Do you know what I'm referring to?
Totally. That is related to this part in particular. So this is IHS, right? And we have IHS here, this dark green line here. Yeah. So if you look carefully at it, in the beginning, so we have a tremolo distribution in which most of the values are considered neutral, but extreme values in which it is based mostly so the values of IHS and NSL will tell you how the derived or ancestral allele will be in the selection, where you have an unusual signature of haplotypes. So those are the three peaks that you can see here. And as you can see, even at neutral mutations, because of IHS erroneously interpret frequencies of either the ancestral or derived allele are selected, but actually we arrive to those frequencies just by genetic drift. It will be more difficult to differentiate between the neutral and the beneficial mutation simulations. So if we just, I'm so sorry that the plot looks like that, but if I just were able to zoom in, you will see that a certain peak of the neutral distribution is overlapping with a positive distribution. So up to a point, and this value roughly coincides with 0.1. So that's the point in which IHS and NSL start to be able to distinguish between those statistics, but not until that point. So it doesn't matter what is the false positive rate in that gap in between. The true positive rate is going to be 0, regardless. That's why.
Okay, makes sense. Well explained. Thank you. So we have more people from your old group grilling you in the chat. So question from Isa Salado. So she says, great talk. Thanks so much. And she's wondering, so I think it's sort of continuing on from what we were talking about earlier. So do you think you could talk a little bit more about the kinds of inputs you need to run Swifter or Swiffer? So she says, do you provide a set of stats ready calculated, or does Swiffer calculate those by itself?
No, actually what I have, so for my simulations, what I output from Slim are VCF files. And those are already phased, so to say. So what I'm working with Slim is using those VCF files and using, for example, CellScan that can work with XP-EHH, NSL, and IHKs. I'm calculating FST with VCF tools and DDAF with a home script. So it depends on what statistic you want to use. So those statistics, for example, the ones that I wanted to show here. So all of this can be studied in CellScan. Also these two. This one is from VCF tools, and actually Hudson FST can be detected with Blink. There's also FLM is also very easy to detect, so it doesn't, or DDF, you can do it with a home script. So the idea is that you have a number of simulations. Let's say 10,000 simulations are VCF files. You have your real data VCF files too. You just run VCF. So with JTK, then you run CellScan. You extract those values from each of the positions of the chromosome. You put them together in a file that is suitable for Swiffer, and then you run Swiffer. So Swiffer doesn't detect them by itself. You have to provide Swiffer with all the statistics that you wanted. If Lisa, I will speak with her. But if anyone else is interested from the group, I can send them an example of the files that I have for Swiffer. That I didn't bring here, but it's very easy to see.
Okay, great, cool. Yeah. So we have another question from Jose Godoy. So again, thank you for the talk. And he's pointing out that, of course, most endangered species will likely have gone through recent periods of intense genetic drift. And he's wondering whether this method would still be able to detect selection in these kinds of cases.
Well, I think that yes, it's possible because, for example, if we have, let's imagine 10,000 simulations working with neutral and beneficial mutations, from those 10,000 mutations, those patterns of genetic drift are going to happen sooner or later in the neutral simulations. So, how to distinguish genetic drift from selected mutations actually is able to do it here. These ROC curves are being performed using both simulations with the beneficial mutation and both simulations with the neutral mutation, and it's actually pretty able to distinguish between the neutral and different demographic scenarios. Still in my simulations, this is something that I didn't mention, but it's great that Godoy asked this. I am asking for the simulation to maintain the mutation, even if it's neutral, in a certain frequency, so that it's more likely to have genetic drift. And actually, Swiffer is able to distinguish between this neutral simulation and all those scenarios in which it's selected. So it's actually able to do it already.
Great. Good news, I guess. Okay, I think we're kind of coming to an end. I'm not seeing any new questions come in. We can give it just a couple more minutes, but if in the meantime, Carlos, you want to add anything, or if there's something, I don't know. So which of the projects that you've listed sort of on your to-do list, which ones are the ones that you're most excited about, or which do you think is going to be the one that will be kind of most fruitful?
I think that the most interesting one would be application to the species with demographic models, or even we can just extrapolate the demographic model. Why? Because I have seen that in the world of computational biology, we want to study models that have been very well studied already. So the projects are being developed use the 1000 Genomes Project, very well characterized human populations with very well studied demographic models, and you can distinguish between different demographic models and so. But actually, and this is why I was so interested in speaking here in EBD, it's just to serve as a bridge between those methods that are being developed for human populations and those studies that are interested in wild species and conservation that are actually not benefiting themselves from all the knowledge of those methods that have been developed for humans. So I would love to try to bring those methods into the world of conservation. I've seen papers from last year that were working with very outdated statistics and working with conservation projects of endangered species. And actually there's a danger, if I can say it again, for overestimation or underestimation of the adaptive potential of those species. So I think it's very important to bring these new methods into conservation genetics. And that's why this is what I think is the most exciting part of the project, and also why I'm so excited to be here talking about it. And some people can bring new ideas how to challenge SWIFR or challenge my models, try to make it as hard as possible and see what is the threshold of detection that we can have, and see if it can still perform previous studies. No?
Great, awesome, sounds exciting. So if any of you have further questions, or you think you have data that you think could be interesting for these kind of models, don't hesitate to reach out to Carlos. And on that note, I just wanted to thank you again for taking the time and waking up extremely early to give this talk all the way from the East Coast. And looking forward to seeing you when you come by for a visit in the near future. All right. Talk to you soon. Take care. Bye bye.
Yeah. Take care. Thank you.